Hey guys, and welcome back to Quantic Academy. So, this will be part 2 of the particle accelerator series. So last time we talked about the linear accelerator. This time we'll be talking about the cyclotron. Okay, so we mentioned the problem with the linear accelerator was the fact that it would get too long. You would require too much space. And so instead of making it just go straight, why don't we make it go in a circle? That will save space, a lot of space. So how do we make it go in a circle? Well, remember one thing. If you have a charge moving in a magnetic field, right? If you have a charge in a magnetic field, then that charge will experience a force if it's moving, okay? So the moving charge will experience a force. And this force is called a Lorentz force. Now, if you don't know what I'm talking about, basic thing, right? If you have a current in a magnetic field, then you have a force on the current, okay? And that force can be determined by using Fleming's left-hand rule, where your index finger points towards the direction of the magnetic field, your middle finger points towards the direction of conventional current, and the thumb points towards the direction of the force, okay? So moving charge in magnetic field experiences force, called the Lorentz force. And the magnitude of that force is given by QVB, where Q is the charge, V is the velocity of the charge, and B is the magnetic field strength, or also called magnetic flux density. They mean the same thing, okay? And this is only true if the charge is moving perpendicular to the magnetic field. What does that mean? Okay, suppose the magnetic field is into the page. X means into the page, okay? And then you have an electron here, okay? Now the electron is moving this way, for example. Okay, now if I use Fleming's left-hand rule, the conventional current will be this way. Magnetic field direction is into the page, so my index finger will point into the page. Conventional current, middle finger point where the current is pointing, and the force points towards this way. So Lorentz force points here. Okay, now you look and see one thing. This is the direction it's moving, okay? But the force is perpendicular to the direction of motion. What does that mean? Well, remember when you have centripetal motion, circular motion, the acceleration, which is the same direction as the force, is usually parallel to the radius of the circle. It points towards the center of the circle, so it's parallel to the radius, okay? And the velocity is tangent to the circle, right? Because the direction is moving. And so the force here is parallel to the direction of motion, parallel to the velocity. And so force here perpendicular to velocity, force here perpendicular to velocity. And so that means this will cause the electron to go in a circle. Okay, it will go in a circle. And now the Lorentz force acts like a centripetal force. And so if you want to find the radius of the circle, just use the centripetal force equation. mv squared over r is equal to qvb. The v cancels. You get r is equal to mv over qb. So that's the radius of the circle. So what you have seen here is that you can use a magnetic field to bend the charge and keep it in a confined space. Okay? So that's the principle behind the cyclotron. You use the magnetic field to bend it. But you still want to accelerate it often. You still want to give it energy. So how do we do that? That's why we have two electrodes, we call it. 2 Ds. Okay? And we connect it to a power supply. So one side will be positively charged, one side will be negatively charged. Now let's use a proton, since we use many electrons already. The proton P+. Positively charged proton. Now if I have a positive here, a negative here, that'll create an electric field. And so the electric field will move will point towards here, and the electric field will accelerate the proton. The electric field accelerates the proton across the potential difference. Let's say the potential difference is V. Okay, and so it will gain energy. The proton will speed up, gain energy. The energy it gains is work done as QV. So that's the energy gain, where Q is the charge of the proton. Okay. Now, when we get here, where I'm circling, then we want the proton to go back through this gap, because this gap is where the electric field is. That's where it gets accelerated, okay? So what we'll do is we use a magnetic field, okay? And I want to bend the proton this way. And so that means the Lorentz force is here, pointing down. Centripetal force points down. And so if I use Fleming's left-hand rule, I get that the magnetic field points out of the page, okay? Out of the page. And a circle with a dot means out of the page, okay? So the magnetic field will cause the proton's path to bend and it'll move in a circle. Remember the radius of deflection is here, r equals mv over qb. Okay, but now when it comes here, look at this. The electric field is still pointing this way. So if the proton were to cross the gap, then the electric field will be pointing opposite to the direction of the proton moving. And so it will actually decelerate it. The force will be in the opposite direction, and so it causes it to lose speed and energy. We don't want that. So we want to change the direction of the electric field. So therefore, we want it to be positive here and negative here. So we can accelerate the proton again and give it more energy. Well, how do we do that? Well, what we can do is we can just change the polarity. It's quite simple. Use alternating current. Use alternating current and just change the polarity. Okay? And so now this becomes positively charged, this becomes negatively charged. And so now the electric field direction will be like this. And so it will accelerate the proton again. So the proton will accelerate, move across here. And it will deflect again due to the magnetic field. And then the alternating current will switch the polarity, becomes plus, and this becomes minus. And accelerate here, and keep going round and round and round, each time getting energy. Okay? Now, since it crosses the gap twice before it returns to its original electrode, right? It crosses it once to get across, and then it crosses it back to get back to where it was. It crosses twice. Each time it gains energy of QV. So in one full rotation, it gains energy of 2 QV. Just remember that, okay? Now, what's the time period of one rotation? Well, the time period when you have centripetal motion, because this is basically circular motion, is 2 pi r over v. Now if you substitute r equals mv over qb, this cancels out, you get 2 pi m over qb. And mass of the proton is constant, charged proton is constant, magnetic field is constant, so the time period is constant, okay? Time period is constant. Now, what about the radius? R is equal to mv over qb. M is constant, q constant, b constant, but v is not constant. The proton is accelerating, it gains speed, v increases. So that means the radius must increase. And as you can see, well, not really as you can see, but the proton will start to spiral out. It will start to go like this, spiral outwards. And so eventually it will escape the cyclotron, okay? And so we put usually a tube here, calculate where it will exit and use that to direct it onto a path and hit a target, okay? Whatever you want to do with the particle. Or what we can do is we can increase the magnetic field, because R equals mv over qb. If I increase the magnetic field, my velocity increases. If I increase the magnetic field, then it will counteract the change in velocity. And so the radius will be constant. And so I can keep it going in a constant path. And that's what we call a synchrotron. And in this way you can accelerate it much further, because you're given it much more time to accelerate it before it leaves. It doesn't even leave, because you keep increasing the magnetic field. Now, synchrotron also accounts for relativistic effects. Now, when a particle goes really fast, it approaches the speed of light, then things change when you get close to the speed of light. Time slows down, everything's different. If you want me to make a video on it, I will. Let me know in the comments, okay? So things change when you're near the speed of light. Time changes, for example. And I'm not going to derive the equation, but basically the time period becomes this. This is what the time period becomes. Okay? Now this term, as you get closer to the speed of light, this term increases. So if I want to keep the time period constant, I gotta increase the magnetic field. Okay? So how does a synchrotron account for relativistic effects? Just increase the magnetic field. And they do that by using electromagnets. That's how the Large Hadron Collider in CERN, Switzerland, the biggest particle accelerator in the world, that's how it functions, okay? Alright, so that's it. Thank you guys for watching to this episode. Hope you enjoyed it. If you did, leave a like and stay tuned for part 3 of particle accelerators, where I talk about particle detectors. Goodbye.